what we saw yesterday was few examples in EEC fit, what are the difficulties one may face and the difficulties in interpreting the data or interpreting the value of the elements. When it is negative, how do we interpret it? When we have an inductance or capacitance, how do we interpret it? I want to show you one or two examples on EEC fit. Okay. So, yesterday we saw that the definition of RT, charge transfer resistance, and polarization resistance, the definitions are different. At infinite frequency, the impedance given by the reaction is called charge transfer resistance. At 0 frequency, it is polarization resistance. I want to show an example on how to use that information for making good initial guesses in the EEC. We saw this example. See, if I take a Voigt circuit and use that to model the Faradaic impedance. So, I am not using the Voigt circuit to model the entire impedance. I have solution resistance here, I have solution resistance as R solution, CDL is the capacitor, ZF is the Faradaic impedance, which I am writing as R0 plus R1C1, R2C2 and so on. If we do this, can I tell what the Faradaic impedance is going to be when the frequency is very high? When frequency is very high, capacitor will act as a short circuit. That means R0 is going to be charge transfer resistance. When frequency is 0, capacitance is basically open, it is cut off. That means R0 plus R1 plus R2 and so on, Rn. So, sum of all the R0 to Rn here, R0 being still part of the Faradaic impedance, that is going to be polarization resistance. Only R0 is going to be charge transfer resistance. Normally, I will not need many, I will probably use 1 or 2 or depending on the number of features I have there. But in general, if you have a Voigt circuit based on capacitor and use that to model the Faradaic impedance, you have a relationship between them. Instead of capacitor, I can use an inductor. Inductor based circuit, here if I say frequency is infinity, the impedance of an inductor is going to be j omega L. So, when omega tends to infinity, ZL tends to infinity. When omega tends to 0, ZL tends to 0. That means, when we go to very high frequency, charge transfer resistance is going to be R0, this is broken plus R1 plus R2 until Rn. So, because at high frequency this is an open circuit. At 0 limit, nothing is going to go through this, it is going to short circuit through this and through this and through this. It is going to see only the first resistance that is present there. Which means if I use a Voigt circuit based on inductor, I know the relationship is here. Now, if I use a Maxwell circuit here means this. So, I still have R solution, C1 here is AA capacitance. So, it starts at R1, R2C2, R3C3 and so on. One resistance and then pairs of resistance and capacitance are arranged in this fashion. So, the circuit below is used to model the entire system including the solution resistance and AA. In this case, if I give 0 frequency, this capacitor becomes open circuit. So, 0 frequency, all the current has to go through this only. So, polarization resistance is R1. If I use infinite frequency, capacitance basically offers 0 impedance, in which case this becomes short circuited, this becomes short circuited, and we have set of resistances in parallel to represent the Faradaic impedance, which means at infinite frequency I can write 1 by RT is 1 by R1 plus 1 by R2 and so on until Rn. Normally, I will not again need 10 elements, 15 elements for this. I do not think you will have impedance with so many features in common cases, but 1 or 2 or 3 cases you can have R1, R2, R1 will anyway be there, but R2, R3 and so on, you can use this. You have a relationship. I will show you an example to illustrate how you can use this information. Instead of Maxwell with capacitor, if I have Maxwell with inductor, zero frequency, this is going to be short circuited, correct. So, 0 frequency means Rp. At the limit of 0 frequency, I can say Rp inverse is going to be R1 inverse plus R2 inverse and so on. Infinite frequency, this is open. Infinite frequency, the inductance will not allow any current to go through, therefore, this becomes charge transfer resistance. So, the expression for charge transfer resistance in the Maxwell circuit with inductor, if I am able to fit the data to this circuit, I can right away tell charge transfer resistance is R1. If I fit it to this circuit, I can right away say polarization resistance is R1. Now, I have not mentioned anything about the capacitance being positive or negative. Okay. The impedance of a capacitor is 1 by j omega c. When omega tends to 0, regardless of the value of c, whether it is positive 10 millifarad or minus 10 millifarad, this will go to infinity. So, I can use positive value, negative value, it does not matter. This relationship is still valid. And the next possible is ladder circuit. Ladder and Voigt will look similar, except that here starting with R1 onwards, we are taking this as a Faradaic impedance. This is solution resistance, this is AA capacitance. Or in fact if you want, you can call this as R solution C0 and then write this as R0, C1, R1, etc., etc. It does not matter. We are going to anyway put numerical values here. Now, if I say this is the Faradaic impedance, if I give infinite frequency, this is the short circuit current that comes from here will just go through this, it will ignore everything here because it is short circuited. So, at infinite frequency R1 is going to be equal to charge transfer resistance. If I give 0 frequency, it is broken here, it is broken here. So, it has to come here, pass through this, any other resistance. So, I am going to get R1 plus R2 plus R3 and so on to be polarization resistance. So, when you come up with a circuit and fit this, you should first think what would happen if I go to infinite frequency for the Faradaic part, what would happen if I go to the 0 frequency. Okay. That helps us get good estimate for some of the resistance values there. And if I use of course with inductance, you can arrive at similar conclusions here and say at 0 frequency one of it is going to be short circuited, here at 0 frequency this is short circuited, in infinite frequency this is going to be open. So, if it is short circuited, all current will go through this, if it is open, no current will go through this, and you can come to conclusions on relationship between these. Now, later we will see that if you have a reaction like this, it is possible to get impedance spectrum like this. At different DC voltages, we will get 3 different spectra here. Now, I want to fit it to this circuit. I have 2 capacitance loops, so I am going to use one Maxwell circuit like this. Solution resistance is more or less 0. This is artificial data of course, so I have made it as 0. Double layer capacitance we have to get. This resistance and this resistance we need to get. Now, I can use the knowledge that this represents the Faradaic process. At infinite frequency, this first loop where it hits, that is more or less where the charge transfer resistance is. The second loop hits the real axis here, that is where the polarization resistance is, because solution resistance is 0. Otherwise, I need to take the distance here and say that distance in expressed as ohm or ohm centimeter square will tell me the charge transfer resistance. Starting from this point to this point is the polarization resistance. If instead of this it is shifted like this, I can't call this as polarization resistance, this is Rp plus R solution, this is R solution. Resistance or impedance between these 2 points tells the polarization resistance. Now, here because this point is 0, I can simplify it and say this is Rp. Now, in the circuit, what is Rp? When I give 0 frequency, current will not pass through this, current will pass through only this. Therefore, if I am taking this data, I am going to estimate it and say I will start with an initial value of 400 or something close to this. Where does it hit here? Okay, this is 200, this may be 100, this may be 80. Of course, If you have access to the data, you can go in little more detail, zoom in and then check. I will say this is roughly 80. Now, what is RT from the circuit? If I give infinite frequency, this is going to be short circuited. That means it is R2 in parallel with R3, correct, and 1 by RT is going to be 1 by R2 plus 1 by R3. Now, I have an estimate for R2. I have an estimate for R3 also now. We can give this as initial guess and ask the program to optimize. Instead of giving the circuit and say optimize and give me, if you are lucky it will give you the values, fine. If not, you should not say this circuit is not a suitable circuit. You should look at the values, give appropriate initial values to the best extent possible and then ask it to fit. In fact, you can fix the value of RP if the data has come all the way here. If the data has stopped here because beyond this let us say it is noisy, you can still estimate where it is going to go and give a value like this. Let us say you have a impedance data which has third loop, then I have to use one more R4 C4. I still use RP from this, no problem. RT if I want to use, I have to write 1 by RT equal to 1 by R1 sorry R2 plus R3 plus R4. Now, I can't guess two values from this, but still I can say choose one value, the other value has to be such that the sum here is still valid. So, although I can't choose R3 and R4 very correctly, initial value if I choose R3 some value 100 ohms, 10 ohms any value, R4 I can choose it such that the first charge transfer resistance will still meet, and then from there I should start optimizing.
So, how do we know there are multiple loops?
When you see visually,
No, like how do we know how to find RCT in multiple loops?
location where this hits, because this is solution resistance, correct. If you take this, this is representing the Faradaic process, means reaction. This is solution resistance and this is CDL, double layer capacitance. Okay. Now, at infinite frequency, we know the process will have only simple resistive behavior. It need not be R2, it is not R2 here, it is sum of all these things at infinite frequency. ZF at infinite frequency should come out as a resistor. When it comes out as a resistor, this is where it is going to behave. Then when you go to lower frequencies, other capacitor or inductor, whatever that element is present, that will also show up and it will have loop like this, etc. Where the first high frequency loop hits the real axis or tends to hit the real axis is your estimate of RT based on the data. Now, all these simplifications I can use when that Voigt elements or the Maxwell elements are made up of capacitors only or inductor only. If we use a circuit which mixes up inductor and capacitor, we can't get this simplification.
Sir,
Yeah.
can you repeat once? Yes, our solution is 0, right?
In this case, yes.
That is why you are taking 80, RT as 80.
Yeah.
If our solution is some value,
Let us say 50 ohms is our solution. Okay. It actually spectra starts here, it goes here, this is 100, this is 0. Then RT is actually 50, solution is 50, RT is 50, and I will just make up this story and say it comes here, this is 150, this is 200. RT is 50 ohm, this is 150, but that is RP plus our solution. Therefore, in this example I will say our solution is 50, RT is another 50, of course, these are all with whatever appropriate units, RP is going to be 100 ohms, because solution resistance is shifting this entire spectrum to the right, we see 150. So, you should subtract the R solution and then you can estimate RT and RP very easily by looking at the actual values, but that is not such a difficult thing, you do not have to really move the spectrum. You measure the low frequency limit and remember low frequency limit is going to be Rp plus R solution. You estimate where the first capacitive loop is going to hit the real axis. Sometimes you may get data which goes like this, then you will have to guess like this, it is roughly there, and then of course fit it and see where it comes. Does it make sense? Yeah.
Yesterday you gave an example when the thing loops back and forms like an inductor.
Yeah.
So that time you take that point as the RCT or the RT if it hits it first. You take the
Yeah.
axis.
Okay. So I will draw here and show you. This is one example. I am assuming it is settling here. Okay. This is another example. This is another example. This is another example. In all these cases, we assume the points, frequency points settle at the location where I am just marking. This is solution resistance. This point is RT plus R solution, and if this is 0, we will just call it as RT. This is Rp plus R solution. This is RT, assuming solution resistance is 0. I am going to skip that phrase now. I will assume solution resistance is 0 and I will say this is Rp. This is RT. It starts here, comes like this and then forms a loop. It can form a loop like this, it can form a loop here, it does not matter where is it going to hit the real axis. If only a resistance is there, it is projected out there, and this is Rp. This is RT, this is Rp. We have data like this. This point is going to be RT. We have data like this and we can simulate it, meaning we can show a reaction which can give you a spectrum like this. This is RT, this meaning where it hits here. I am not very sure whether it hits right here or right here, that is okay, I do not remember it well, but maybe I will draw it little better. I will project it here and call this as RT, wherever it settles that is Rp, provided solution resistance is 0. Otherwise, you just have to add the solution resistance all this and that is what you would get. Now, RT you can get it from impedance spectroscopy. Rp you can get it from impedance as well as other techniques. Now, I also want to show you that instead of using a Maxwell circuit with capacitor only or a resistor only, I am going to draw this. In one of the earlier classes, we had looked at a spectrum which looks like this, and then I showed you if you take a circuit like this, it does not seem to fit well. Zimpin says it is not able to fit it, well it does not say that, it fits it, but we are not happy with the fit. Whereas, instead of this, if I use negative values for these to model this inductive loop, then I am able to fit it very well. And then we use the equivalent circuits, say these two circuits are equivalent, meaning capacitor and resistor in series in parallel with the resistance can be modeled by a resistor, inductor and a resistor, and then we found that this resistance has to be negative, minus 200 or 290 ohms or some such number. Whereas, if you look at the data, it never goes to negative in the real axis, correct. So, when you mix up and get an inductor and capacitor in a circuit to represent Faradaic impedance, you cannot get a simple expression for polarization resistance or charge transfer resistance. Previous cases where we looked at the examples starting here, one of them will be simple equation, that is R0 is RT. I use a slightly different representation, R0 is Rp. Other one is sum of this or inverse of this resistance is going to be sum of inverse of all these things, etc. I use Maxwell circuit with capacitor, one resistance can be identified quickly. With inductor, another resistance can be identified quickly. This is RT can be identified, previously Rp can be identified. Ladder, again I can identify Rp or RT quickly. If I have a mixed circuit, when I give 0 frequency, this is broken, but this is short circuited. So, I have two resistance in parallel at the minimum, I may have more elements. If I give infinite frequency, this is short circuited, but this is broken. So, you should not mix inductor and capacitor when you are modeling Faradaic impedance part. If you have film on the surface and you are modeling the film plus reaction, then you may get inductor and you may not have a choice, that is different. When you assume there is only simple meaning a reaction without any further film formation and so on, then this part which represents Faradaic impedance, it is better to keep it as set of inductor or set of capacitor. Usually we keep it as set of capacitors, but you should not mix up. So, if I use this and say this set of 3 spectra I can model using this circuit, I can guess the value of R2, I can guess the value of RT, not guess the value of RT, yeah I can guess the value of RT, from that I can guess the value of R3 and then optimize it, I can get the circuit fit. Not just that, I want to show you another example. Okay. This is a data that I have synthesized. This is something we have seen before. Okay. It actually comes from a data which looks like this, which you can model using solution resistance, double layer capacitance, and either I can use resistance, inductor. I can model this, or I can do something similar for the first component and I will say resistor, capacitor, allow negative values. Either case I can model it. What I have done now is to add some noise to that artificially. Okay. And then what happens when we fit it? This is the original data which looks like this, supposed to come nicely and sit here, but if it comes very nicely and sits there because I have given artificial data, then confidence interval in all parameters will tell I have 100% confidence or it is 0% standard deviation. But I want to show you what happens when you have a real data. This is of course not real data, but noisy data. Okay. In the Zimpin, I can use this circuit model. Any other software you can use, it is okay, you will get pretty much the same result. It fits it and then says, yeah, this is the fit, of course it is noisy, the data is noisy, fit is okay, and this has come from artificial data, it does fit well. I have created random noise and added over this, so it is going to be on the average, it is going to be still following the original value with slight deviation. I want you to look at the values of the elements. The resistance, first resistance here is 10 ohms, it is 1.03 10 power 1, relative standard error is 1.3%, capacitor is 20 microfarad, that is also coming correctly 2%, 125 ohms is the resistor here. So, this resistor is 125 ohms, standard deviation is 1.4%. That means, in this representation I know infinite frequency current will not go through this. So, charge transfer resistance here is 125 ohms. Look at the confidence or the percentage relative standard error in L, it is about 22%. Low frequency data has lot of noise, therefore, it is not very sure that this is the correct value, it has come up with a value of 361 Henry, resistance is about 490 ohms. So, it has got a value for this resistance here. In the inductor it is 361 Henry, resistance is about 490 ohms. We are not very confident, it is okay, 8%, 9%, 20%, in that range we have the relative standard error. So, I am confident about RT, I am not confident about RP, because from this if I have 1% error in RT and 8% error in the next element, I have to take them in parallel to estimate RP. I will get poor estimate or I will have less confidence in that, because one of the elements has low confidence, the final value also will have low confidence. Actually, it depends on how much weightage each element contributes to the final value, but unless you do the calculation very carefully, you will say I can estimate RT well, I have some problem in estimating the R2 or whatever that second R is, I do not have that much confidence in the L, I do not have that much confidence in that R, therefore, I may not be able to tell you RP very well. Data also looks noisy in that region. Now, instead of this, I can use C. except that I have to say that this has to be negative, only then I can model. So, I have given it negative and ask it to model, it will fit equally well, because those circuits are actually equivalent. The percentage standard deviation, relative standard deviation is different now, because of the way that each element is related to the impedance. So, we have 23-24% relative standard error for the capacitance. We have 8% standard error in the resistor, which is associated with the capacitor. This value, the one associated with Rp, we have confidence now. So, now we have good confidence in the value of Rp. Rp is close to 100 ohms. Rt was close to 125 ohms. It starts at 10, it hits close to 135 here, that means 125 ohm is the Rt. It hits close to 110 ohm here, that means 100 ohm is the Rp, but it is not apparent that you have reasonably good confidence in Rt and Rp, but you will have to use different circuits to get that quickly. If you want to estimate Rt from this effectively at infinite frequency, this is going to be a resistor in parallel with another resistor. So, let us say Rt inverse is Rp inverse plus we will call this as R2 inverse. If I am confident about this value, it is within 1%, this is 8%, I have to do it correctly. I can say this contributes mostly to this contributes less to this, but when you do it in one form meaning capacitor based, you have to do the weighted averaging and say even though this element has lot of error, for the total calculation it does not contribute much, therefore, I am still confident. What that means is, when you look at real data and analyze, you have to look at the confidence interval for the parameter values to know whether your circuit is good, whether you have to do one more element, you have to do it with care.